I'm Dr. Jeffrey Summers. I'm a emeritus chair and professor at East Tennessee State University in the Department of Internal Medicine. We're going to talk today about test characteristics. And by the test characteristics, I don't mean that, is it wet chemistry or dry chemistry or those sorts of things, but instead talking about the test performance, sensitivity, specificity, positive and negative predictive value. Those are going to be the focus of our topic. Okay, let's get started. We're going to be looking at sensitivity, specificity, positive and negative predictive values, and by the end, you should have a pretty good handle on what these measures actually do. And we start off, you're typically taught about this grid that has true and false positives and negatives. And when initially setting up the sensitivity and specificity for the test characteristics, you just fill those in with the values that you find. If you do this test on a couple hundred people, you find that 80 have true positives, 60 have false positives, 88 true negatives, and 23 false negatives. And then you have to remember what are the formulas to get you sensitivity and specificity, which, given that that's kind of a memorization task, that's not ideal. But in this case, the sensitivity, which is true positives over the sum of the true positives and the false negatives, ends up being 0.78, and the specificity is 0.59. Those are not great numbers, but let's move on. The next way that people have sensitivity and specificity explained to them is spin and snout. Spin means that you use specificity to rule things in, and snout means that you use sensitivity to rule things out. But that really does not help with understanding the concepts that are involved here. So how about a way to remember sensitivity and specificity that also helps with understanding what they actually mean? That's the goal of this video. And it's that all of these are actually the accuracy in specific populations. Sensitivity is the accuracy of the test in those who have the disease. In other words, in those who are ill. Specificity, accuracy of the test in those without the disease. Positive predictive value is accuracy in those who have positive tests. And negative predictive value, accuracy in those with negative tests. Okay, so how does this make it easier to remember all this stuff? Well, if you remember that you are supposed to be sensitive to those who are ill, human kindness. So if you're going to be sensitive to those with the disease, then all the rest of them fall into place. Specificity becomes the accuracy in those without the disease, and positive and negative predictive values for those who have positive tests and negative tests, respectively. So let's look at this sensitivity in a little more detail. Here are some example questions that reflect sensitivity. How many people with lupus, in other words, who have the disease, have a positive ANA? That would be what is the sensitivity of the ANA. How many people with DVT have a positive T-dimer? In other words, those who are ill have a positive test. How many people with carotid vascular disease have a positive carotid bruit? It doesn't have to be a lab test. In this case, it's a physical finding. How many people with pneumonia have an abnormal chest x-ray? So it can be radiology also. And what percentage of the time is the echocardiogram abnormal in those with hypertrophic cardiomyopathy? Specificity examples. So now we're talking about the accuracy of the test in those who do not have the disease. So how many people without lupus will have a negative ANA? How many people without blood clots will have negative D-dimer? How many people without carotid disease will have no carotid bruit? How many people without pneumonia have a normal chest x-ray? And how many people without hypertrophic cardiomyopathy have a normal echo? Makes for kind of funny questions. You know, the phrasing on specificity ends up being odd, but you do have to just remember that you're talking about who does not have the condition, who will then have a negative test. Specificity is also tied to the false positive rate. So this actually makes it a little bit easier to do those questions. Another way to think about specificity is that it's 1 minus the false positive rate. So if your false positive rate is 10%, the specificity is 90%. If the rate of false positives for D-dimer is 35%, the specificity is 65%. That makes the questions a little bit easier to talk about, but you do have to remember that it's 1 minus that false positive rate. So then, positive and negative predictive values. Note that sensitivity and specificity actually do not depend upon the prevalence. In the case of positive and negative predictive values, they very strongly depend on the prevalence. If the disease does not exist in the population, such as Martian flu, then all of the positives are false positives, and the positive predictive value is 0. So positive predictive value is the true positives over all the positives. Negative predictive value is the true negatives over all the negatives. So let's look at an example here. Cologuard. I hope I don't get sued. The incidence of colorectal cancer, according to the CDC, at age 50 is about 60 per 100,000. The sensitivity of Cologuard, according to their own website, is 92%, and the specificity, again, according to the Cologuard website, is 87%. Let's take a theoretical cohort of 100,000 people that we're going to screen using Cologuard. 60 of those will have colorectal cancer, because we got that statistic from the previous slide. Sensitivity of 0.92 means that of those 60, 55 will have a positive test and 5 will be false negatives. The specificity of 0.87 means that of the 99,000 plus that don't have colorectal cancer, you have almost 13,000 that'll have false positive tests, while 86,000 and change will have true negative tests. So the positive predictive value, it's those true positives, 55, over all the positives, which gives you a positive predictive value of 0.004 or 0.4%. Negative predictive value would be the true negative over all the negatives, which is 99.99%. So a negative Cologuard you can pretty well trust. But they do recommend only doing this in people of normal likelihood. So, basically at that rate of that 60 per 100,000. Positive test, very unlikely to actually have colorectal cancer. Okay. D-dimer. Another one that we talk about a lot as far as its sensitivity and specificity. And why is it a good screening test but not a great test for ruling in pulmonary embolism? with the usual cutoff values, and that's actually a very important point. The sensitivity is 97% and specificity 41%. Pooled data, and I'm talking about for pulmonary embolism, not including DVT. Well, what about the prevalence? How do we know what the prevalence is when we're about to do this test? Well, there are some criteria that can give you ballparks, Wells and Geneva criteria, and there's also good data that suggests that if you use your gut, basically this person really looks like they're having a pulmonary embolism. Well, the gut is very good, but it does tend to overestimate. So if we use what is the average prevalence of pulmonary embolism in people who present to your emergency department and where you're suspecting pulmonary embolism, the overall prevalence is about 30%. Let's do this again like we did for Cologuard. We take a cohort of 100,000 with a prevalence of 30%. That means 30,000 will have clot and 70,000 will not. Of the 30,000 who have clot, that 0.97 means that 29,100 will have a positive test and there will be 900 false negatives. Of the 70,000 people who don't have a clot, 41% will have a negative test, while 41, which gives you 28,700, while 41,300 will have false positives. That's a huge false positive rate. The likelihood that someone with a positive test has a clot is then the true positives over all positives, which works out to 41%. Likelihood that someone with a negative test has no clot is then the true negatives over all the negatives, or 97%. So you can be fairly comfortable if you get a negative test that the person does not have a clot. But you cannot be comfortable that a person who has a positive test is going to actually have clot. So why is the specificity so dismal for the D-dimer? And this comes down to a question of where do you put the normal cutoff? There had to be a decision made as to how high the level of little D-dimers, how high that has to be in order for it to be termed positive. And the idea here was to try to make the test as sensitive as possible so that you can use it to rule out a clot, but recognizing that when you raise the sensitivity, there's a correlation that occurs that also lowers the specificity. And this comes to our last topic, which is receiver operator characteristics curves. And that is that the false positive rate, which is 1 minus the specificity, plotted against the true positive rate, that, which is essentially the sensitivity, that if you plot those, you can choose anywhere on that curve to be your cutoff for what's normal or abnormal with the test. But let's look at that blue line. If you pick a true positive rate that is very high, then you end up with a false positive rate that is also very high. The concept of receiver operator curves dates back to World War II and the radar installations on the south of England. They found that if they turned up the gain on the antennas on these radar installations very high, they could pick up every plane that was coming over from Germany, but they would also end up picking up flocks of birds. Turn it down, you're going to not pick up the flocks of birds, but you also may miss some of the planes coming over. So the idea is to set this high enough on the true positive rate, make it very sensitive, though you then sacrifice and get a high false positive rate as well. And remembering that specificity is 1 minus the false positive rate. I hope this was educational. I hope that you enjoyed this, and this helped you with understanding sensitivity, specificity, and the very important positive predictive value and negative predictive value, which are critical for properly interpreting the results of tests. Leave me comments in the messages below. Thank you.